So, ayan, meron tayo dito ang actual diode characteristics. So, remember datasheet? So, most probably this one is taken from datasheet. Okay? So, if you notice, makikita sa region nito kung nasaan yung ating no bias, reverse bias, and forward bias condition. Okay? So, asan kaya ang ating no bias? Again, sa no bias, no current, no voltage. Saan ba dito yung no current? Ito yung current, y-axis, x-axis is the voltage. No current is somewhere, andito. Okay? So, andito yung ating, um, this is not no bias. Kasi mayroong voltage, oh. -10, -20. Ito may bias to. Okay? So, malamang, nandito yung ating reverse bias condition. Meron kang negative supply ng voltage, however, wala kang current because baliktad siya. Okay? Ganun yung diode kapag kabaliktad, walang current. So, dito si reverse bias. Saan kaya yung no bias? Saan ba dito yung walang voltage? This is 3. Ito, pataas na pataas yung voltage. Saan ba dito yung wala? Of course, nandito sa 0. So, nandito banda yung ating no bias condition. Wala kang voltage as well as wala ka ring current. Okay? Sa forward bias, habang tinataasan mo yung voltage, sometime medyo wala pang current na nag-flow, ano? Pero habang pataas na pataas yung voltage, palaki na palaki yung voltage, unti-unti ring nagkakaroon ng current flow sa ating circuit. Okay? So, hindi naman siya ano no, pag ganun talaga yung graph kasi hindi naman siya linear talaga na habang palaki na palaki yung voltage, pataas na pataas din yung current. Hindi naman ganun. Depende din naman yun sa circuit kasi. Okay? So, this is our actual diode characteristic based on as reflected on our graph. So we now have here the term majority and minority carriers. So two currents through a diode. So kapag may nag-flow ng current sa diode, it could either be, it is dalawa. Okay? Meron tayong tinatawag na majority carriers and minority carriers. Dalawa yung nagpo-flow ng current. Ibig sabihin, may isang papunta doon sa kabila, yung isa sa kabila. Okay? Pero of course, mas malakas yung may isang mas malakas talaga yung flow. Okay? Andun yung majority carriers. Ano ba itong majority carriers? So, the majority carrier in N-type material are electron. Okay? Kapag yung material mo ay N-type, of course, kasi mas marami doon yung electron. So, ang majority carriers, mas marami, merong ang karamihan sa nagfo-flow, ganun lang yung term. Karamihan sa nagfo-flow is electron. Okay? Kapag P-type naman yung material mo, karamihan sa nagfo-flow is holes. Kasi mas maraming holes. Okay? Sa minority carrier, baliktad. Okay? Yung N-type material mo, meron kang holes as your minority carrier. Ibig sabihin, hindi lang puro electron yung flow, meron ding konting holes papunta sa other direction. Mga ganun. For your p-type, meron kang electrons baliktad din as your minority carrier. Okay? So, we are now ready for Zener region. So, most probably this is something to do with the Zener diode. Okay? Tingnan natin. Right. So the Zener region in the diode's reverse is in the diode's reversed bias region. So yung Zener region, so kanina meron tayong 'di ba reversed region, reversed bias region. 'Di ba dito banda 'yon? And dito yung forward bias region, tama ba? At dito yung no bias region. Remember? So meron pang additional. Ito yung tinatawag na Zener region. Ano itong Zener region? Andito daw. Oh my God, but my Zener. So at some point, the reverse bias voltage is so large that the diode breaks down and the reverse current increases dramatically. Ayun. So, kapag binaliktad, di ba sabi natin kanila, pag baliktad yung diode, walang flow ng current. Tama ba? Pero sabi niya, kapag in-increase, pag binaliktad mo yung diode, pero in-increase mo yung voltage, okay, persistent ka, Talagang niligawan mo siya, in-increase mo pa rin, in-increase yung voltage. Ang nangyari, nag-breakdown siya. Nag-breakdown. Oh, nag-flow na yung pumayag. Okay, 'di ba kasi ayaw ni Dayo ng baliktad? Ayun, persistent ka. Tinaasan mo yung voltage hanggang sa pumayag yung diode. Nagkaroon na ngayon ng flow of electrons. Nagkaroon na kayo ng current. Pero take note, ano na-notice nyo? Dito yung current is dahan-dahan. Dito yung current is bigla ang tumaas. Pero sa kabilang direction, reverse sa other direction. Okay? Take note, nag-increase yung current dramatically. Dramatic yung increase niya. Eto, agad-agad. Wala nang hindi katulad dito dahan-dahang nagkakaroon ng flow dito, biglang nag-flow. Okay, so the maximum reverse voltage that won't take the diode into zener region is called the peak inverse voltage or the peak reverse voltage. So meron tayong tinatawag na peak inverse voltage. Ito yung maximum voltage. It is the voltage before this one. Sorry, excuse me. So ito yung maximum voltage bago siya mag-breakdown, bago niya ma-reach itong zener region. Okay, ang tawag mo doon sa maximum na yun is peak inverse voltage or peak reverse voltage. Peak, kasi siya na yung pinakamataas na ano, bago niya ma-reach yung zener region, bago siya mag-breakdown. Okay? So the voltage that causes a diode to enter the zener region is called zener voltage. So before yung zener region, before yung zener voltage, meron ka munang peak inverse voltage or peak reverse voltage. Ito yung maximum na hindi siya pupunta sa zener region. Kapag tinaas beyond the peak inverse voltage or peak reverse region, voltage rather, pupunta ka na sa zener voltage. Kapag na-reach mo yung zener voltage, ayun, pumunta ka na sa zener region. Again, meron ng dramatic increase of current. Nag-flow na, pumayag na yung iyong diode. Pwede pala yun. Consistency is the key, diba? Okay, so we have here our reverse bias voltage. So the point at which the diode changes from no bias condition to forward bias condition occurs when the electrons in the holes are given sufficient energy to cross the p-n junction. This energy comes from the external voltage applied across the diode. Ayun. So itong forward bias voltage, tingnan mo. Hindi porket from zero, 'di ba? Hindi porket nilagyan mo ng konting voltage, may sufficient na flow ka na agad ng current. Hindi. There is some time, kailangan mo ma-reach na certain amount of voltage din para meron ka ng sufficient flow ng current. Okay? Ang tawag mo doon, meron kang required na forward bias voltage. Alright? Para saan ba tong forward bias na voltage? Naalala nyo ba to? Ito. Itong forward bias, kailangan para ma-break itong region na to, para makapass through yung ating mga charge. So, kailangan niya ng enough, hindi lang basta voltage, but enough voltage to break through this barrier here. So, for different type of semiconductor, meron silang requirement. No? Meron silang kanya-kanyang forward bias voltage requirement. For gallium arsenide diode, kapag ka, di ba yung diode is junction, PN junction, di ba? Again ha. Sana yan? Wait. So, tandaan muna natin. So, for GaAs, gallium arsenide, meron kang 1.2. For silicon, 0.7. Germanium is 0.3. So, balikan natin yung sa taas. Yung junction. Ito. Diba ito yung junction, PN junction? Diba this is just semiconductor, pero yung half ginawa mong N-type, yung half ginawa mong P-type. Okay? So, kapag yung semiconductor na gamit mo dito ay germanium, okay, para ma-break itong barrier na na-form dito, or depletion region, para ma-break yun at makakos ng flow ng electricity, kailangan meron kang at least 0.3 volts. Kapag silicon yung gamit, kailangan meron kang at least Ilang volts? At least 0.7 volts. Konti lang ano? Kapag gallium arsenide yung ginamit, kailangan meron kang at least 1.2 volts. Okay? So, ito yung mga different forward bias voltage requirement para ma-reach na yung conduction region. Okay? And also, meron din tayong temperature effects. Okay? So, remember yung crystal lattice. So, somehow, meron pa rin nagfo-flow doon ng electron because of temperature. Okay? Because of room temperature. At room temperature, somehow kaya niyang mag-ano doon, kaya niyang mag-knock off ng some amount of electron. Konti lang naman. Okay? So, ibig sabihin yung temperature, it affects your electrons. Okay? As temperature increases, it adds energy to the diode. It reduces the required forward bias voltage for the forward bias conduction. Okay? Kapag di ba meron tayong forward bias? For example, sa silicon, kailangan madating mo yung 0.7 bago siya mag-conduct. Okay? Yung temperature, nakakatulong din siya. Kapag mataas yung temperature, instead na 0.7, wala pang 0.7, nagko-conduct na yung diode mo. Kasi, temperature matters. Ganun talaga sa mga electronic devices. Temperature plays an important role that has to be considered talaga. Okay? It increases the amount of reverse current in the reverse bias condition. Kapag higher yung temperature, yung reverse current natin sa reverse bias condition ay nag-i-increase din. It increases maximum reverse bias avalanche voltage. Again, it increases maximum reverse bias avalanche voltage. Okay? So, with high temperature, medyo tumataas yung ating reverse bias avalanche voltage. So, for the germanium diodes, ilan nga ulit yung forward bias ng germanium diode? For germanium, you have 0.3. Mababa lang. Gallium arsenide, 1.2. Sakto lang yung silicon. So, for germanium diodes, these are more sensitive to temperature variations than silicon and gallium arsenide diodes. So, itong germanium, hindi siya masyadong ginagamit. Although semicon siya, hindi masyado because, you have to remember, because medyo sensitive siya sa temperature. Kung baga konting init lang, ayun, nag-iiba na ng konti yung kaniyang behavior because nga of temperature effects. And you don't want device that becomes faulty kapag umiinit na. Diba? So, kaya hindi masyado ginagamit yung ating germanium diode. So, next is we have the resistance level. So, semiconductors react differently. Yung mga semicon natin, iba yung behavior niya kapag ginamit sa AC or DC current. So, kasi iba yung behavior niya, nagkakaroon din tayo ng 3 types of resistances. Kapag meron kang DC na supply ng current mo, DC current, you would have also DC resistance. Kapag AC, meron ka ding AC or dynamic resistance. Kapag ka DC, of course, kapag ka DC yung current mo, yung static, di ba ito, direct current, so nagkakaroon ka rin ng static resistance. Kapag ka alternating current ka, bago-bago yung current pa, nagkakaroon ka rin ng dynamic resistance. Tsaka meron din tayong tinatawag na average AC resistance. Titingnan natin siya bawat isa. So for DC, we have the static resistance. For specified applied DC voltage VD, the diode has specific current ID and a specific voltage. Kapag ka DC yung sinupply mo sa ating diode, okay, kapag ka DC, meron din tayong, of course, fixed or static resistance na nakukuha, which is just equal to V over I. This is still our Ohm's law. V is equal to IR, remember? Oh, ganun pa rin. Of course, your resistance mo would depend on your levels of your voltage and current. Take note of this formula. That is for your DC or static resistance. For your AC, dynamic resistance, eto na yung formula mo. In the forward bias region, hindi na siya simpleng ganito lang. Because this one is only applicable for DC. Kapag ka AC na, ito na yung formula mo. Your RD or your resistance mo, dynamic is 26 millivolts over ID plus RB. The resistance depends on the amount of current ID in the diode. So, of course, yung resistance mo, depende pa rin siya sa ID. Still, parang V over I pa rin siya, pero meron ka ng RE. The voltage across the diode is fairly constant. So, yung voltage mo sa... Kaya 26 millivolts to. Kasi 'di ba kanina, this is VD. The voltage sa diode, depende kung ilan yung supply. This one sa AC, meron ka ng fixed na 26 millivolts. Okay? So, that is at 25 degrees Celsius. So, yung RB mo ranges from typical 0.1 for high-power devices and 2 for low-power, general-purpose devices. In some cases, RB can be ignored. So, sometimes, kasi 0.1, minsan 2. Mababa, ano. So, masyado siyang mababa. So, usually, hindi na siya sinasali. So, usually, the formula is 26 millivolts over ID na lang for AC dynamic resistance. In the reverse bias region, yung RD, pagka of course baliktad siya, reverse bias, yung resistance mo, open circuit siya, no? Yung resistance mo, kasi pagka open circuit, walang nagfo-flow na current, ibig sabihin, napakalaki or napakalaki ng resistance, as if infinite. So, kaya yung RD mo dito is infinite. The resistance is effectively infinite. The diode acts like open. So, kapag ka-infinite yung resistance, as if open yung ating diode. And of course, kapag ka-average AC resistance naman yung kinuha mo, you just get the average, okay? So your resistance average is just the change in your VD from point to point, of course, and the change in your ID, okay? So, I think this is the last one. Okay. Ito lang i-explain ko. The rest, you have to read it. Okay? So, sa diode equivalent circuit, so itong diode natin, pwede natin siyang i-model into like this. Okay? Meron siyang equivalent circuit. So, itong diode na ito, still, meron kang current dito papunta pa. Meron ka rin sign, positive, negative. May VD. Okay? Tsaka meron ka ditong constant voltage supply na 0.7. Tsaka meron kang R average. And this is equivalent to 10 ohms. Then you have your ideal diode right here. Actually, ang tawag natin sa model na ito is what we call the piecewise linear equivalent circuit. Okay? Tandaan. This is your piecewise linear equivalent circuit. Ito namang isa, ang tawag natin dito, merong tatlong model kasi. This one is simplified kasi medyo complex siya, no? But this one is piecewise, called piecewise. This one is called the simplified equivalent circuit. Simplified siya. Wala na yung resistance. Ano, you only have your ideal diode and then you have your 0.7. Kumbaga, kapag ganito yung model ng ating diode, if you notice, wala na yung ano dito na graph, dahan-dahang pataas. Because wala na yung resistor. Dito kanina, kapag ito, this represents the more actual. Okay, mas approximate to. So, itong resistor cause this one to dahan-dahan siyang umakyat. So, dito, because wala na yon, ganito lang siya. Okay. Pag na-reach yung 0.7, because this one is ideal, conduct agad. And of course, this is our ideal equivalent circuit. Siya lang talaga. Okay? So, wala kang VD, wala kang voltage drop kapag dumaan yung current dito, assuming na on the right entrance siya, right direction, edi conduct agad. Wala kang tinatawag na voltage drop. Okay, so these are called models sa ating diode. Again, for the diode model, meron tayong piecewise, linear, meron kang voltage, resistance, and ideal diode. This is the graph. The curve is most probably be due to this resistance. And meron kang, number 2 is simplified equivalent circuit. Simplified, meron ka lang 0.7 volts dito, and tsaka ideal diode. And this one is ideal. Okay? So, saan ba magagamit yung mga models na yun? Okay. So, usually, you are going to use a simplified model kapag ka yung resistance ng whole resistance ng network mo is greater than the R average resistance value ng iyong diode. Kapag ka masyadong malaki to kumpara sa kanya dito, edi you can just omit this one. Pwede na ganito na yung ano niya, um, model niya. Okay, kapag ka yung R ng network mo is mas greater than the resistance level ng iyong average ng iyong diode, at saka yung voltage dun sa network mo is much greater than the voltage total of your diode, then most probably you can also omit this one. Kaya pwedeng ideal na lang. Usually pag malalaki yung values mo, you can just use ideal. Pagka sobrang maliliit yung mga values mo, this would matter. So, sinasali siya. Okay? So, that's it for this chapter. Again, I think I really suggest that you read the book, you really understand. Anyways, this very detailed discussion is just on the first chapter. The rest will not be this much. Medyo lang, pero important kasi na alam niyo to, naintindihan niyo talaga to para mas ma-appreciate niya as you go on. So, good luck guys. You can do it. Just think of your future in your future board exam. Right? Bye.